I didn't really introduce you. I just basically sent everybody your Twitter feed and said that everybody that is in consciousness should listen to your Lex Friedman interview.
Okay. So I'm Joscha Bach. I'm a cognitive scientist. Mario and me know each other back from our joint time that we spent in Osnabrück. At the University of Osnabrück has a department for cognitive science, as you probably know. And we were back then, before cognitive science was famous and while it was still cool, and enjoyed our time very much together. And since then, life has sent us down different paths. And I'm currently living in the Bay Area because I always went into academia to build artificial intelligence, the real one. That was the topic that interests me most, basically how minds work. And when I went down the path of trying to figure out how minds work, I basically settled on the insight that the best way to figure that out is to build one. And so I ended up in artificial intelligence mostly. And in my view, artificial intelligence is two things. It's a philosophical project, first of all. This is in some sense how it started. It's about the mathematization of the mind. And it's also an engineering project. And the engineering project is the automation of data processing. And 99% of what you hear when you hear about AI is this latter project, the automation of data processing. And the philosophical project is disjoint from that. It's insignificant compared to the larger engineering project and the applications of artificial intelligence. But it's the most interesting philosophical project that there is, and the most important one. And it's a very risky and fascinating project, and in many ways the capstone of philosophy. And the only thing that's left to do, because if you've done it, you can leave philosophy to the machines. So let me open my slides. Where are they? Here they are. I don't know if you discussed the imagery debate in cognitive science. It was a big topic in the 1980s where Jerry Fodor and Zenon Pellichin ran against Stephen Coslin and argued about whether the thinking happens in language or in images. And Coslin argued that there is the imagery is the crucial thing, and he gave a number of substantial arguments that could be supported by experiments. For instance, there's interference between thinking and perception. And there is certain characteristics when you try to imagine a scene and you zoom out of the scene, and certain features are salient in your imagination rather than zooming in, and so on. These are all things that don't happen in language. On the other hand, Fodor and Pellichin argued that all thinking happens in the language of thought, and this language of thought needs to be systematic and compositional. Otherwise, you could not have infinitely many thoughts in the way in which we do. And if you'd only had images, you would not have infinitely many, and they would not be arbitrarily compositional and systematic and allow the degree of inference. And they never could resolve their differences, but it gives rise to a very interesting question. Basically, how does thinking work? How do we experience thinking to work? Are there interpersonal differences in how thinking works, and how can we understand a system that thinks? Ludwig Wittgenstein is famous for having triggered the linguistic turn in philosophy. And I suspect that he's mostly been misunderstood in philosophy. In his famous Tractatus Logico-Philosophicus, which is a very beautiful 75-page long thought, without any kind of argument or literature references or anything. It's basically just a single thought. He wrote this thought down with the intention of helping people who basically had the same thought and want to see it properly expressed. So he was not setting out to convince philosophers of anything. Instead, he went down a certain path and went this down with all the necessary consequences, and you can take it or leave it. And the Tractatus starts with, the world is everything that is the case. And the world is the totality of facts, not of things, and so on. So the world is determined by the facts, and this basically is a set of definitions. And what he tries to do in these definitions is to formalize natural language in such a way that it means something, that you can define what truth is in these languages. And what he does in this project is that he preempts Marvin Minsky's logicist program of AI, the attempt to replace thinking by a formal language by several decades. And he was not the first one to go into this direction, but there were a number of people who came before them. I just mentioned that I think that AI is a philosophical project. And this philosophical project can be understood when we understand that philosophy is the domain of all theories or of all models, and it starts out with natural languages. And because natural languages are so poorly defined, it's very hard to say something in philosophy that's true, but you can actually prove that it's true. And mathematics is the domain of all the languages. So if you want to study what's true in a language, you start out in mathematics. And mathematics starts out with the simplest languages, those where truth is clearly defined, and these are the formal languages. And mathematical languages make it easy to say things that are true compared to natural language, but they make it very hard to say some things about the world because these languages are so simple, right? You might think why mathematics is hard. No, it's so simple that we know everything about what something means in mathematics. And when you want to say something in mathematics about the real world, you have to simplify the real world so much that you can say something about this in the simple mathematical languages. And typically it means that you create a toy universe with extremely simplified physics or extremely simplified ways of counting and so on. So you can now apply your mathematical language to this toy universe and then hope that the things that you discover in your artificial mathematical universe still hold true within the universe that you interact with. And if we want to get philosophy and mathematics to meet, we have to narrow this gap. And a number of philosophers tried to do that, and basically they failed. And what they discovered is we need to find a mechanical way to do this. We basically need to automate this process that our mind is doing when it gets mathematics and philosophy closer to each other by formalized means, right? So we formalize the process of formalization and the process of observing the world and abstracting it into theories. And we have to formalize both directions until they meet. And this domain in the middle is basically a mechanical mind. And one person who discovered this train of thought was Gottfried Wilhelm Leibniz. And he had this idea of a universal calculus that allows us to express every statement in the form that we can calculate. And in some sense, the discourse would then become a calculation. And when I first got introduced to this idea by my philosophy teachers, they laughed at it because I think they didn't get it. They didn't take Wittgenstein's linguistic turn. They did not understand the nature of that project. Frege continued with this, with the Begriffsschrift, Formelsprache des Denkens. And Wittgenstein was one of the later proponents of this train of thought, of a train of ideas in philosophy. Mathematics itself can be understood as a universal code library. It's been maintained for centuries. It has no versioning. It has a pretty much unified namespace. That's why it uses lots of the Unicode alphabet. And it has no central maintainers, which is really amazing, right? There is no code of conduct that was necessary to make it happen. Beyond what people could infer should be done if you want to do the right mathematics. So basically, it's something that can be inferred automatically, autonomically. It's not a social thing. It's a thing that is done by highly autistic people for a very long time. They managed to figure things out, not in the world of right and wrong, but of true and false. Yet, there was a problem at the foundation of mathematics. And this problem was basically how to ground mathematics in first principles. And the way in which we typically ground mathematics in first principles now is that we define logical languages. And in these logical languages, we define number theory and everything else. And these first principles, to get them right was very hard. And typically the way to define number theory and the computation that we can then do in number theory that we can use then to do logic again and so on, were defined use set theory. And set theory, you can define numbers as the cardinality of sets. So how many members does a set have? And what Cantor discovered is that there are issues with that, especially when you come to the infinities. imagine you have the set of all subsets of a set. The set of all subsets of a set has obviously more members than the set itself. Where imagine you have a set with 4 members, 1, 2, 3, 4 has 4 members, and the set of all subsets would be the combination of all these 4, right? So this would have be 16. And you can easily show intuitively that the set of all subsets is always larger than the set of all set itself. And now, if you have an infinite set, you have a weird situation, right? Infinite set has infinitely many members, but if you take the set of all of its subsets, all the combinations of the members, it's dramatically larger. So you now have several infinities, larger and smaller infinities. Right, that's fine. We can define different types of infinities. It's a little bit counterintuitive, but we can probably get used to this. And people did this, and Cantor came up with different kinds of omegas, which were different kinds of infinities, and did some kind of infinity arithmetic over them. But it doesn't stop there, unfortunately. If you look at the set of all sets, which is the total set, right, the set that contains all sets, how many members does it have? Right, it has obviously a very large infinity as members of its set, but you can again make the set of all the subsets of that. That would be even larger, but it would already be contained in the total set. Right, now you have a contradiction. You basically now have proven that the total set has a different number of members than the total set, because the total set also contains a set of all of its subsets and so on. Right, and at infinitum, so it never really stops. It does not converge to a fixed value. And so David Hilbert said, we need a different foundation for mathematics. Please, mathematicians, go and find something else that works, that doesn't lead us into any kind of contradictions. And then famously, Kurt Gödel came along and demonstrated that this doesn't work. There is no solution to this problem. Right? What Kurt Gödel showed is that we cannot build a machine in mathematics, in any kind of mathematics, that runs the semantics of mathematics as it's classically defined without breaking. Right? Mathematics is a specification without implementation. You can specify it, but you can prove that you cannot implement it. It doesn't work. And this Unentscheidbarkeits idea that Gödel has discovered was something that was misunderstood by Gödel himself and by many people who came after him. Gödel was convinced that the notion of truth that existed in mathematics, which is stateless, eternal, doesn't depend on the sequence of steps that you have to go through, is objectively real. He was a Platonist in this sense. He thought that mathematical truth exists, and it exists in the way in which it was defined. And when he would prove that his formalism couldn't reach that truth, he was devastated. And in philosophy, there's a long tradition, starting with the philosopher Lukács, who tried to understand Gödel's proof. And they basically understood Gödel's proof as mathematicians have shown that mathematics, it's impotent to deal with reality. Right? There is something that mathematicians can prove that they cannot do. And this gives an advantage to people who cannot do mathematics, philosophers, namely, who don't have a formal education. And this intuition was something that is incredibly popular with philosophers to this day. Right? There is a long tradition in trying to digest Gödel's proof, and Gödel's proof is understood as an artifact that stands in the Museum of Mathematics. It's deeply mysterious. Nobody really understands the consequences. You can see amazing articles about this to this day, and books about this to this day. And there are very few philosophers who have understood the consequences of Gödel's proof and what it meant for mathematics. It meant a turn in mathematics in the last century. It meant that we had to rewrite part of the code base of mathematics to make it implementable. And this was a discovery that Church and Turing and many others made. We can build a different kind of machine, a computational machine. And it cannot run the classical mathematical semantics, but it can run all of computational semantics. And it's a very beautiful result, because what we can see is when we look at the actual mathematics that have always been done, they've always been computational. It always worked step by step. There was never any infinity that mathematicians could use in mathematics and derive the result from. And the consequence is that it also changes the way in which we look at the universe itself. So in the universe itself, there are no infinities. There is unboundedness. It's not the same thing as an infinity. Unboundedness means that you never stop and get a final result. There's never an end. You can always continue. There is no bound in the number of digits in pi. Right? You can plug a function into your nearest sun, and you can run that function until the sun burns out. You always get new digits of pi until the sun has burned out. But you will never have a process in nature that relies on having known the last digit. Right? There is no infinity. There is no mechanism that can perform infinitely many steps and gives you the outcome. And this is the change that you need to do in mathematics to make things work. Right? It's change from the classical mathematics to computation. And what Gödel and Turing could show is that the assumption that you can have functions that run through infinitely many steps and give you a result lead into contradictions. And this was basically the constructivist turn in mathematics, the most important result of philosophy in the last century. And interestingly, one that most philosophers did not understand and did not continue on. And if you look at philosophy these days, I think it's unfortunately in a state where it's mostly idea history. Has historical value. The largest foundation that funds philosophy these days is the Templeton Foundation, which is mostly driven by religious values, and they have a budget of, I think, $30 to $50 million a year for philosophy in the world, right, outside of some people having tenure. So it's very little money that still goes into philosophy. And this means that our societies basically think that at this point, philosophy is irrelevant, which was unthinkable to me when I started studying philosophy. I was just frustrated by the state of it. And at some point, the mathematician Misha Gromov told me, you know, the last philosopher was actually Charles Darwin. He was the last one who could connect dots. And after that, this was everything that you could do in an armchair. After that, you needed formal methods. You needed to do mathematics. And so philosophy after that has only been writing. To Gromov, somebody like Russell was a writer, somebody who was able to connect ideas that had already existed in philosophy and present them in a new way so people could understand them better. But all the major thoughts had already been thought. And I think there is something to this perspective of Gromov. He might be a little bit radical, but I found that whenever I study ideas and I have new insights, they never new. It's just that the party that I discover gets smaller and sometimes further back. But these ideas are all have been had at some point, and there are relatively few new ideas that were only had in the last century. And most of these ideas are about computation. And so I do believe that there have been new things, but they have not been thought within the departments of philosophy, and they have not been integrated in philosophy. The philosophers have lost that train of thought. And there are some philosophers like Floridi who are trying to do a philosophy of computation, but he is a complete hack. He doesn't get these ideas at all. He's impersonating a philosophy professor at Oxford. He's super good at this, but there is no philosophical insight. It's all a pretense that it does. The intuition that philosopher has serves these existing intuitions and then imports the concepts from information science and so on to inform that. I think that a complete philosophy that is built on a computational basis is one that is in some sense a philosophy of AI. It's one that makes information primary and the manipulation of information primary. And this is something that is not a popular idea in philosophy. What Turing discovered, also what he got famous for, is the Turing machine. The Turing machine is a way to understand computation by changing data on a tape, an infinite tape or an unbounded tape that you can move backwards and forward. And you have a read-write head. This read-write head is taking one symbol from that tape and then looks up in a table based on the state of the Turing machine and the character that it reads. It looks up in this table and goes into a new state, the Turing machine, and writes a new symbol on the tape. And then it moves one step to the left or to the right. And what he could show that this is sufficient to do all computations that can possibly be done. And this is an invention of the computer. And there have been many other ways to define the computer, and they're all equivalent. And a different way to define the computer was done by Alonzo Church at the same time as the Turing machine, but completely unrelated. And this was the lambda calculus. Lambda calculus sounds very scary because there's like Greek letters in it, lambda, and the word calculus, which makes it even more scary. But it's actually very simple. The lambda calculus is trying to explain all of computation by search and replace on strings. You all know search and replace on strings. If you ever try to fix some wording in a long Word document, you all used it, or in programming code, right? Search and replace is super easy. And it's only doing that. And what it does, it looks all for all the instances of the lambda y. The y is lambda marks the y, and then it replaces them in the string that comes after the dot. In this case, the string is x and brackets yz, and it replaces, in this case, all the instances of the y with ab. So it's really just a way to define the string replace. And the lambda is an artifact that happened because when Church defined all this, he marked this thing that he wanted to do replacement with making a small roof on top of it, right? So a little angle drawn on top of it. And he didn't have that on his typewriter. So he left an empty space before that, and he made the angle before that for the typesetter. So in the final manuscript, when they print this, they could make this open triangle that he was originally drawing on top of it before it. And then this was translated into the Greek letter lambda, this open triangle. And so this thing was named the lambda calculus. This is the only reason why it's typography. It's only he tried to make a little roof over the y, that was it. But it's actually just a search and replace calculus. And with the search and replace calculus, you can do the Turing machine. You basically can express all the operations of the Turing machine with these expressions, with string search and replace. And you can also do the opposite. You can write programs that run on the Turing machine that do search and replace on the string. So you can show they have exactly the same power. And the insight that all computational machines that can be built have the same power is called the Church-Turing thesis. And this is one other big important result, that all the computational machines, once they reach universality, once they have a certain minimal power to become equivalent to a Turing machine, can do the same stuff until they run into resource constraints, right? So until you run out of memory, you can do the same stuff. So what Turing did was to prove something about mathematics. Turing invented the computer, en passant. And Wittgenstein was a pupil of Turing. He took classes with Turing. He was a student. No, other way around. Turing was a pupil of Wittgenstein and got these ideas from Wittgenstein and worked on them. And Gödel didn't have this idea that he could invent the computer because he knew that he already had a computer. And the computer that he had was Peano arithmetic, the natural numbers. It turns out that the natural numbers themselves are a kind of computer, right? It's defined from some axioms, and just by following the axioms, you can perform operations. And the way in which he used the integer numbers, the natural numbers, as a computer was that he found a mapping from logical expressions into integers or into natural numbers. And he basically did this by looking at the fact that if you try to write down a logical expression, you have to write it down in an alphabet, and you can basically assign numbers to every character in the alphabet. And then you can perform an operation that assigns a unique number to every sentence that you create by combining logical symbols, right? And now you basically have a way to translate an arbitrary logical statement into an integer, into a number. And this was a complicated process that involved prime numbers and exponentiation. It looks very elegant, and people call it Gödelization. Today, we would use it very differently. We just try to take the logical expression and translate it into ASCII code or Unicode, and then write it down as a bit vector in the computer memory, right? And what he would show is once you translate your logical statement into numbers, you can also define computations, operations on the natural numbers that evaluate these logical expressions. So there's basically a formula on this natural number for every logical operation that you can perform that performs these logical operations on the natural numbers. And then you can take the new number that you get and translate it back into a logical expression. And you can show that you now computed the value of the logical expression. So what you could basically show is that at some level, the Peano arithmetic is equivalent to performing a logical language. There's an equivalent between logic and numerical arithmetic, right? And it's something that he discovered before the discovery of the computer, which is based on the same idea. It's the Turing equivalence between certain dialect of logical languages and a certain dialect of number theory. So mathematics is the domain in the classical sense of all specifications, and computation is a subset of mathematics. It's the domain of all the mathematics that can be actually implemented, that can be realized, it can be created as some computational paradigm. And I think to exist means to be implemented. A very interesting way to think about computation are the automata. And in a way, the Turing machine is an automaton. And the lambda calculus is also a kind of automaton. And a very beautiful automaton is the game of life that was discovered by John Conway in the 1950s. And many of you might know it. It's defined on a rectangular grid. So it's just a lattice where every cell has exactly 8 neighbors, like on a chessboard where every field has exactly 8 neighbors. And we define these fields as potential cells, like a biological cell. And each of these fields contain exactly 1 cell. And then we have a bunch of rules. If an empty field has exactly 3 neighbors, then a new cell is born in that field. And if a living cell, has exactly 2 or 3 neighbors, then it's going to stay alive. But if it has fewer than 2 neighbors, it's going to die because it's too lonely. And if it has more than 3 neighbors, then it's going to suffocate. So it's also going to die if there is too many neighbors. And so if you start to take an empty field and you draw a few cells randomly, what you see is an evolution of these cells. Basically, some cells get born in new spots, other cells are dying in some spots, and sometimes you get periodic patterns. Right, so these are patterns that you get. It looks quite beautiful. It's super easy to implement. You just need to implement these 3 rules, and what you get is this stuff. And it always ends in a periodic state, ultimately. And the periodic state is either some long period, or it's going to die. So it's the period of 1, where nothing moves anymore. One thing that was very interesting was the glider. A glider is a pattern that is self-replicating in such a way that it moves itself along through the resulting space. And there are several types of gliders that could be discovered in the game of life. They're basically horizontal gliders, which are sometimes called spaceships, and these diagonal gliders. And of course, they can go into all directions, and they can bump into each other and interact with each other. And an interesting side effect of that is that you can implement a computer in game of life that can run again the game of life. Right, so you see gliders that interact with other gliders and bump into each other.
I use this video in my dynamical systems course. Yasha, just to let you know, there's a question by Daphne after this session when you have a second.
Yeah, so that's the game of life and game of life. Daphne, you have a question.
Yeah, so maybe I missed it, but so you just talked about, using, if I understand correctly, using language to do computation, and then you started talking about the game of life, but what is exactly the link between what you talked about before and then transitioning to the game of life, where I think there's like an emergence of complexity, but could you elaborate on that?
Yes. So the way in which we define a language is in mathematics, where we have the simplest languages, to define a formal system in which we define meaning. And to create languages, we need to have a machine that is able to evaluate the language, to parse an expression in the language, and then to understand the meaning of that language, which is a function that is changing some content. And so what I'm trying to do is to give you an intuition about how to do this, how a system can work that can manipulate symbols, arbitrary tokens, to execute functions, and eventually to compute functions that give you meaning. And I'm trying to get there step by step. So we'll get there.
But then you need the definition of meaning, I think.
Yes, and we'll get there.
Okay, sorry.
No, it's not. Don't be sorry. It's a very good question. It's very interesting that we can have basically this game of life is some kind of language with 3 rules. In the same way as Peano arithmetic is a language that is defined by 5 axioms. And these 5 axioms give you the natural numbers and all the operations over the natural numbers that you can construct step by step from this axiomatic system by having rules that explain to you how to make that extrapolation. And in the same way, if you have these 3 rules, you can define an automaton, this game of life, that produces all these dynamics together with the starting state, which is the initial state of the grid. And it turns out that just by having these 3 rules and a suitable starting state, you can build the game of life in game of life. And what Gödel did is that he basically created a mathematical language, and he did this by defining all the symbols in his mathematical language, which were and or, and a variable, and how to get from one variable to the next variable, and so on, if you want to enumerate them, and to have a sequitur, which means how to get the consequence of a premise in a way. He defined this very simple language by mapping it to symbols that could be translated into numbers, and on functions over these numbers that would give you the combination of these logical symbols, the result of that, in such a way that you could basically compile your logical expression, your string of logical symbols from your notation into numbers, then perform a computation with natural numbers on these numbers, and then translate it back into logical symbols, and you would have the result. And he could prove that this result would have to be correct. Right, so he basically showed a way in which logic can be performed using numbers, if you only have numbers. And the numbers that he used basically are an automaton. It's an automaton defined over the axioms of Peano arithmetic. But you don't need to use Peano arithmetic. You can also use the game of life for doing that. Or you can use bits in a computer. When they all are Turing machines, they all have the same power. This is the idea that I'm trying to get across. Another example that is much more complicated is Minecraft. Right? Minecraft is a world that you can visit. It's a virtual world, a very simple one. And this virtual world is an automata world that is made from voxels, from blocks that can interact with their neighbors. And Minecraft has the property that you can build computers in it. There is a particular kind of mineral that you can mine out of the ground, redstone, and you can refine the redstone into switches and wires. And you can arrange these wires 3-dimensionally in Minecraft in blocks and arrange switches between them. And in this way, you can build computers in Minecraft. And people have actually done that. And at some point, there was the question, would it be possible to run Minecraft in Minecraft? And people thought, yes, theoretically, obviously. But at some point, somebody actually did it very recently.
I saw your tweet when it came out. I was like, yeah, that makes sense. But what an ordeal.
Yes. So this guy had written a machine already, which he called Chungus. Chungus was his CPU that could run computation and had some RAM. But for running Minecraft, he did more than 256 bytes of RAM that all had to be painstakingly created in Minecraft as blocks. Of course, he wrote some scripts that helped him with writing or creating the computer, but still it had to be built. So there's years of combined research efforts in how to build computers in Minecraft, and then months into actually building this computer. It had graphics memory, and it has a GPU, the Amogus GPU.
It's insane.
And a controller. And then he wrote a version of Minecraft that is a bit more compact than the big one, but it could run with this reduced resolution in 2 colors on that screen. And it's sped up 2 million times, the video. Because of course it's insanely slow to run this in Minecraft.
So you guys have to think that, you know, we cannot compute Minecraft in our brains, right? But we can make a Minecraft computer inside a Minecraft game that speaks to our intuitions about what Minecraft is. I find the way that the circle is closed so amusing. Sorry to just barge in.
So obviously you could also write a Minecraft that runs in Minecraft that runs in Minecraft, but that one would be 4 trillion times slower. Not just 2 million times slower. And but you can always emulate a computer in another computer, and the computer can also emulate itself. And the way in which this was discovered was because Gödel wanted to make a proof in mathematics about mathematics. And so he needed to discover or to invent a foundational language in which he would be able to describe all of mathematics, or at least the subset that he wanted to have, and then recreate this language inside of that language. So he could say something about that language is inside of that language, right? You cannot in logical language talk about things outside of that language. How would you? You can only refer inside of a language to things that can be expressed in that language. So you need, if you want to make proofs about the language itself, build a language that can recreate itself in itself. And that's true for all the computational languages. And the first time that was ever done was in Gödel's proof, which is very beautiful. So to sum up, computation is constructive mathematics. It's the part of mathematics that can be implemented. And the universal computer is relatively easy to make. You can make it for many automata. And all the universal computers that have the power of Turing machine have the same power until they run out of memory. And every biological cell in our organism contains a Turing machine. And the biological cell is the simple system we know in nature that contains a Turing machine. And it's like almost literally a Turing machine with the tape with the read-write head, right? The DNA with the replisome on top of it. And it's mostly written by a slow evolutionary process, but via the evolutionary process, it can get almost arbitrary programs inscribed on it. And the DNA in our cells does not contain a blueprint for the organism. That's not the right way to think about it. It's an operating system for the cell, right? And all cells are the same, just with a different operating system. All the cells that exist in nature are the same biological cell. All cells in nature originated from the first cell. And the first cell has never died. It only divided. And all the cells in our bodies are split off from that first cell. It's amazing when you think about this, that the entire life on Earth is still the first cell, just split up and differentiated by having different code written inside of it, different operating system. And this operating system is a set of subroutines. They're called genes. And most of the genes have been discovered many, many million years ago. Right? The set of useful subroutines exists for a very long time. It's very rare that new genes are discovered by evolution. They're just combined in different ways and turned on and off in different ways. That's also a very fascinating result. Right? So with these amino acids, the cell writes down programs, and these programs are interpreted. And depending on the situation that the cell finds itself in, these programs are looked up and executed, and they tell the cell how to adapt to a certain situation, or how to differentiate into a different type of cell, or how to copy itself, or how to die. And these are basically the operations that the cell has to do, to copy itself, or to differentiate itself in a slightly different cell, or to adapt to a situation by performing some regulation. Mario?
So would you say the DNA, what part of the cell machinery is the formal language? Is there an actual formal language? Because there?
Yeah, I think that the DNA is very close to a formal language. There is, it's not just the code itself. There's also some information stored in the way in which the DNA is folded. And the DNA is not the only tape in the cell. There's also RNA and probably other stuff in the soma of the cell that contains information that maintains state for the cell. But if you squint, then basically the DNA is a tape with a read-write head in the Turing machine. It's just that there are a few more tapes in addition, so the tape's a little bit longer than that.
I was wondering whether like the cell physical context influences how the read-write tapes work in non-linear ways. But
of course.
preferably
Yeah,
not though, right?
But nonlinear sounds always very amazing, right? But linear just means that you have a value that can change almost continuously, right? So you change in small steps, and you get small steps in the change in the outcome. That is the idea of linear. And nonlinear means you have discontinuities, you have gaps in that, and that basically means you have an if-then.
Or saturation.
Right, so nonlinear sounds more complicated than linear, but it's actually the opposite. When we talk about nonlinearities, we both mostly mean if-then. And right, when you, for instance, look in the room and you count the objects, this is a discrete number. It's not a continuous number of objects in the room, right? This is nonlinear. And linear stuff is when you have something that changes by small amounts, like the width between your hands when you move them apart and close together. And in nature, everything ultimately is integers. When you zoom in, everything resolves into individual particles and into Planck length intervals and Planck time intervals. There is nothing that is completely continuous. Geometry is the domain of too many parts to count. But we live in a world where most of the things are too many parts to count. So we have these geometric approximations. Another thing that that Turing got to was the insight that if everything is either less than a Turing machine or a Turing machine, it follows that minds are Turing machines. Right. So now we have a paradigm in which to understand minds. And this basically gave rise to this project of artificial intelligence that was officially inaugurated by Marvin Minsky and a few others in 1956 in Dartmouth. Basically, computers were around, and Minsky thought that computers can deal with both linearities like dynamical systems and with non-linearities. So we can have arbitrary code, we can reasoning and can have grammatical language in it. And he hoped that in the course of a few years, we might be able to teach the computers how to think. Later, he gave a more close estimate to how many years, between 400 and 400 years. And in psychology, this gave rise to the physical symbol systems hypothesis, which means that you, using a layer of symbolic computation, you can give rise to arbitrary systems that are built on top of it, that include geometric manipulation, perception, reasoning, and so on. And the systems that had been built in this vein were mostly symbolic systems. And these symbolic systems ran into problems later on. And we get to this. Language has several levels at which you can describe them. You have at the lowest level logical languages, and then you have computational languages, for instance, programming languages, in which you can have all sorts of expressions, and you have grammatical languages that human beings are using, and that are mostly not constructive but disambiguating, right? So a difference between programming languages and natural languages is that programming languages start with a tabula rasa. You start with an empty memory. And in this empty memory, you construct everything from scratch, right? You define how to do arithmetic, you define how to do string operation, you define how to do graphics step by step until you get everything that you want. And in a natural language, you already have all these things. You disambiguate between those things. You can construct stuff, but for the most part, I assume that you already have most of the ideas that I'm referring to. And I just explained to you which of these ideas have to be activated right now and how they have to be plugged together to get the current context. And it's a very different way of operating than we do in a natural language, to do with a programming language. And one of the other big fathers of artificial intelligence was Noam Chomsky. But an accident happened. Noam Chomsky and Marvin Minsky lived at the same town at the same time in neighboring departments. Chomsky was mostly at Harvard and Minsky at MIT, but just 2 subway stations apart. And they didn't get along. And so Minsky, for the most part, started to ignore language. And Chomsky, for him, everything that the brain is doing is just get the brain to the right temperature until it reaches the all-important language center. And he never thought about cognition beyond language, which is really perverted if you think about it, right? You have these very big minds that do not want to collaborate, but insist on creating their own independent disciplines that are so stubborn that they never listen to anybody else and think that any kind of contradiction, if it holds water, will occur to themselves at some point in time. So it's not necessary to listen to the critics at all, and they just power through and build their stuff and create a circle of disciples instead of people that interact with them critically and tear down their theories to build new stuff. Right? It's quite beautiful if you look at how this happens and why it happens psychologically. You have these extremely beautiful, highly autistic minds that are so superpowered that nobody else is able to contradict them. And they create these big schisms in cognitive science as a result, because most mortals are too stupid to be able to tell these guys at which point they're full of shit and that they would need to combine their ideas and how. And this happens quite a few times. And it's, of course, not Chomsky's and Minsky's fault that other people were too stupid to tell them when to stop and how to combine their ideas. But what Chomsky was looking at is what he got famous for is, in addition to strong opinions about the Middle East conflict, universal grammars. And universal grammars are the basic idea that grammatical language needs to be innate in human beings and the other animals don't have it. And he built this based on the poverty of stimulus argument, which means he can show that human beings don't get shown enough data to learn language from the data. They discover a grammatical language without having shown how grammar works. And it's interesting because that's quite different from, say, a transformer model like GPT-3. Right? Our machine learning models get enormous amounts of data until they discover grammar and language. And they learn it, but very late. And human beings learn it very, very quickly. And Minsky thought that's because we have special circuits built into our brain that encode how that is done. And these circuits were not quite found, and Minsky revised this idea, what is the innate part? And the current iteration is the minimalist program, which says there's only a merge operator built into the human brain. But it's not clear why chimpanzees don't have that merge operator. The idea of this universal grammar is the least popular contribution of Chomsky to linguistics. And also from the perspective of computer science, I suspect that it's not necessary. I suspect that we get the grammars as a search process. There's an interesting observation that Chomsky has made. If you are a polyglot, if you know many, many languages, and you know maybe something like 14 languages, and you encounter the 15th language, you're not learning very much anymore. You only need to learn the vocabulary, because people who know many languages have seen them all. They have seen the entire space of grammars. And they understand the entire space of grammars, right? It's very difficult to conquer that space of grammars just by learning 2 languages. But when you learn a lot, you basically see all the solutions to grammar. And the problem that grammar is the solution to is how to take a hierarchical, distributed, fuzzy mental representation, some fuzzy hypergraph, and translate it into a discrete string of symbols with a procedure that is learnable. And that can be executed with a stack depth of less than 4, right? Because most people cannot do more than 4 items on the mental stack before they lose track. So you cannot have arbitrarily many levels of recursion or relative sentences. And if you impose these limits, that you want to have a discrete string of symbols and you want to have a stack depth of 4, it limits the ways in which you can define how to arrange symbols into representations. And the resulting space is probably the space of human grammatical constructs that exist in the different languages. So different languages are solutions to all the same problem of translating mental representations into discrete strings of symbols. Why discrete strings of symbols? Why not continuous howling noises? But another problem is learnability. Language is not directly observable. It's mathematical. It hangs in the thin air between speakers. Right? You cannot actually point at language. So language has to be discovered to some degree. In order to make it discoverable, you need to constrain the problem space. You need to constrain the complexity, and you constrain the complexity by imposing this constraint that the language needs to be expressible as a discrete string of symbols. Right? And that makes the problem simple enough to make it discoverable. And that's why human beings can discover language instead of having to learn all of it. They fill in the gaps. They discover regularities and so on. They discover the simple solution as a data compression problem. And I think that's the answer why human beings can learn grammatical language. And the reason why chimps cannot learn grammatical language is probably a different one. I suspect the main reason why chimps don't learn grammatical language is because they don't have a long enough childhood. Human beings are unique in taking a very long time before they go to the next layer. When you have children, you notice that they go through phases where basically they train a layer and then they get the next layer online. In this new phase, they change dramatically. They're also very confused because the world looks very different to them. But it's basically layer by layer trained architecture. And the time until the next layer is trained doesn't depend on how much data you see, it depends on time. It's basically some kind of hormonal switch built in your genetic code that determines the length of each learning period. And each successive learning period takes longer. So initially, the learning periods of your newborn child are days, and then there are weeks, and then there are months. And then the learning periods are years, and eventually decades, until we get the next layer online. So we see these steps in human development in adolescence, and your mid-30s, and in your 50s, and so on, when people basically get the next layer online and understand the world at a deeper level. Before that happens, we are insane. We act based on innate reflexes that happen for no reason that we understand. And so people in their 20s have extremely strong moral opinions, and these moral opinions seem to be completely evident and true to them, but they cannot prove that they're correct. Right? They're compelled to act on these moral reflexes, but they're not able to understand the systems that they're part of yet. And this leads to very interesting confusions, right? And the emergence of ideology on campus and so on based on moral reflexes. And it's not because people are evil and so on, it's because young people are insane because they don't have enough layers online to model systems, right? So it's like babies cannot model the world because they don't understand who they are. They haven't discovered themselves yet. They might not have discovered the notion of goals yet. They might not have discovered the notion of changing goals yet and so on. And you can see at which phases all these things happen. So for instance, a 2-year-old typically goes into a phase where they identify with goals, but don't have a way to turn off the goal if it's not reachable. So they throw tantrums when they cannot reach the goal, because through them, it feels like they're dying. It's not because they want to test the patience of their parents. It's literally because they cannot move to the level where you turn goals on and off, right? And once they get there, they discover that goals are something that are ubiquitous in the universe. Many people have goals. They try to change the goals of everybody around them, and they become these little imperialists that try to change the world around them. What Chomsky got rightly famous for is that he discovered how to formalize grammars. And this was an enormous influence on computer science and on the definition of programming languages and in the ways in which we build parsers for programming language, and a lot of the early work in AI, also in Minsky's vein. And so the way in which he defines grammars is as a for tuple that is a finite set of non-terminal symbols and a finite set of terminal symbols that has no overlap with the non-terminal symbols. A terminal symbol is one that is a final symbol that you cannot replace by anything else. It's your final words in the language. The non-terminal symbols are stuff that you don't see in the final printout. For instance, the symbol verb or noun and so on in the functional sense are non-terminal symbols. So when you write down things, you don't write verb, verb, noun, noun, noun. You only use them as intermediate steps. You say this sentence needs to contain a verb and a noun, and replace the verb and the noun by terminal symbols, by a concrete verb or concrete noun, right? And once you replace them with a concrete symbol, you cannot replace them with anything else because your sentence is finished. And in order to make these translations between these non-terminal symbols into other non-terminal symbols and terminal symbols, you have so-called production rules. There are rules that tell you if I have a set of terminal and non-terminal symbols, how can I replace them with terminal symbols? And you can define an arbitrary set of rules that tells you how to perform these translations. And then you need a starting symbol, which is a non-terminal symbol. So you start out with a starting symbol, and then you apply these rules. And as a result, you get some tree of possible ways in which you can perform these applications. And then you get all the possible sentences, which are infinitely many, or an unbounded number of sentences, right? So, and you can define all languages in this way, all the formal languages at least. And then we get a hierarchy of languages based on the automata that you are using to define this language. And this so-called Chomsky hierarchy starts out with regular grammars, which are just basically simple replacements. And then there are context-sensitive grammars at the highest level, you have recursively enumerable grammars. And they basically, human languages are in this recursively enumerable area. And in order to parse a human language, you need a complete Turing machine to make that happen. So if you look at this hierarchy of Chomsky languages, and I don't go into detail here, if you look at music as a language or animal languages or human languages, you can see that they span different regions of that space of these formal languages that you can define using Chomsky's different types of grammars. You can also go into neural networks and discover what types of neural network learning algorithms can form neural network architectures that can then parse different types of Chomsky languages. And it turns out that all of these different learning algorithms that are used in the neural network architectures ultimately, of course, go down to a finite state machine. And the finite state machine defines the learning algorithm of the neural network and the computer that runs the neural network. So it turns out that everything that we did in computer linguistics using Chomsky grammars and so on over many decades was trash. It was all not useful. We had to discard it all when people discovered how to train neural networks efficiently and at scale. And that basically, that transition happened around 2012 when a team from Google and Stanford got together and trained a network, a neural network without supervision on YouTube frames. So basically, they picked random frames out of YouTube videos and then took a number of GPUs and just looked for patterns with a deep neural network in these YouTube frames. And they discovered automatic categories of images. They discovered faces, they discovered cats, they discovered all sorts of objects without any kind of training. And they had an accuracy and object recognition with neurons that would emerge as classifier neurons of in ImageNet, which is an image recognition benchmark that's still being used, of, I think back then, 16%, which was much better than anything that had been handcrafted before. And now these models have been trained better and better, and they are at superhuman performance, which means that they're able to recognize object categories that most humans don't know, like all the different dog breeds and whatever you want to look at. They are good at discovering this in the training data. And in 2017, sorry, I cut off the two last digits of the year, Ashish Vaswani and a bunch of others discovered the transformer algorithm. And the transformer algorithm is the way to train neural networks by making statistics over what you should make statistics over. So you don't look at all the data in the previous layer when you do your statistics in a neural network. You learn that for any given context, which bits or which nodes in the previous layer should pay attention to. And this algorithm makes neural networks efficient enough to learn many, many types of functions without human intervention. And this especially works with relatively messy domains. And it turns out that natural language is so messy that it has many, many, many exceptions. And many of these exceptions are almost impossible to formalize. People are able to understand language that is quite agrammatical. Right? You take an arbitrary sequence of words and grunts and people interpret meaning into it. And to define all the ways in which we do this using production rules is a very daunting task. And in the past, when people tried to build translation systems from one natural language into another one, they had to find ways to do this almost by hand, right? And then they would do simple statistics over this, but we needed a way to automate all the statistic making. And neural networks are basically a way to do statistics on steroids. So what Vaswani discovered is an algorithm that is scaling with respect to natural language. And you could feed in basically almost the entire internet. The first iteration was using text from Reddit and some literature collections and so on. And the next one was using basically almost every text that was referenced from Reddit and had to score over 3, which had a minimum quality. So it was a substantial subset of the internet. And this thing is just an autocomplete algorithm. It only works by predictive coding. It takes this idea of Friston seriously without referring to it, that all you need to do is predictive coding, minimize the prediction error. The way the transformer is trained, it takes a string of tokens of input words, and then it tries to predict what input word is going to come next. And it's training this thing by updating it on what came next in the actual text. And so in this way, it gets better and better. And it's a very slow process of getting better and better. But if you have $10 million to compute in a very large data center and a very big training set, that's sufficient to use the transformer to get a language model that is at superhuman quality. And superhuman quality means that it's able to imitate style much better than any human being alive. It's not able to get context as well as experts in any kind of domain. But if you are a non-expert in a domain, if you don't know the domain, then GPT-3 is going to get a better text than you are. Here's an interview that I did with Johann Wolfgang von Goethe. The green part is the one that I gave to GPT-3. Only the green part. It's literally what I typed into GPT-3. That's the string that it got. And it was asked to basically continue this string. And the white stuff is what it has continued. Right? So this initial string suggests that this text is part of an interview that a modern interviewer is conducting with Johann Wolfgang von Goethe, who was dead for quite some time. And Johann Wolfgang von Goethe's texts, many of them have been part of the training set. Both English and German texts have been part of the training set. So this thing is able to translate between English and German as part of many, many other things that it can do, all on the course only of string completion. So I found a way to talk to Johann Wolfgang Goethe. He speaks German, me. Johann, could you please translate this sentence into German? The computer is the best model of reality. And it's also interesting that he says JWG, Johann Wolfgang Goethe, in this abbreviation in German. Die Information ist der neue Gott. What does this mean? Information is the new God. Can you explain this? Nur die Information kann uns helfen, den überwältigenden Eindruck der Leere zu überwinden. Only information can help us to overcome the overwhelming impression of emptiness. I see. Aber die Information hat ihre eigenen Gesetze und ihre eigenen Wunder. But information has its own laws and its own miracles. So you can take this GPT-3, you can use it almost for free. There are other language models that have similar quality now that you can even download and use for free on your own machine, if you have a large enough one. And you can have an interview with Hannah Arendt over the end of modernism, or you can complete programming code. And it works on a lot of different type of code, not just human sentences. It also works on music. So for instance, you can translate music into MIDI, and then you can train that thing on MIDI data, and it's going to compose music for you. Or you give a programming code, and it's able to translate C code into Python code, or comments into a verbatim programming code, or verbatim programming code into comments, and so on. And you can use this to support your self-programming. Or you can give it the opening moves of the chess game, and it's going to continue the chess game. At some point, it's going to lose the context and forgets what was on the board. It's not by far not as good as a human chess player, but it's able to play a little bit of chess. Right? It's really amazing what GPT-3 can do. And what you could see between GPT-3 and GPT-2 is that the model became larger by a couple orders of magnitude, and it became better at the same rate as GPT-1 and GPT-2 became better. And the curves are not bending. So if you were to find a couple orders of magnitude more text than the internet contains, this thing was probably still able to learn new regularities. And this idea that just getting more data into the model is sufficient to learn everything is currently referred to as the scaling hypothesis in AI. So that we basically have everything with these algorithms, and we just need to have slightly different loss functions and better training data and more compute, and we get to human level intelligence and beyond. And as I said, in many ways, this is beyond human level. But of course, it's in itself not general intelligence. It's not as general as our mind. There are many problems that cannot solve, that human beings can solve easily. a very different, important discovery that in some sense contrasts with this original question, do we think in language or in images, was the notion of an embedding space. And the embedding space was discovered around 2013 in Word2Vec. Word2Vec was just doing statistics over words in the English language and later on in other languages. And what was discovered is that if we order words only by similarity in the space, we get a multi-dimensional space. How does that work? So if to give you an intuition, I'll give this. Yeah, if you think about how the human brain forms its body map, up to before you are born, even while you're still in the womb, the simplest way to create a map of your body is to do statistics over all the neural impulses that enter your brain via the thalamus. The thalamus is the switchboard between the body and the brain and between different brain areas. And if you do statistics over the incoming impulses, you can learn the statistical structure behind these impulses. And so if you get signals where two signals, the two incoming wires are always on and off at the same time, it probably means that they refer to exactly the same nerve, for instance, in your body surface, so you can merge them. And if they're almost always the same, they're probably neighbors, right? If you have two nerves on your body surface that are directly adjacent, touch nerves, and you touch your body surface, very often they will be touched at the same time. And so just by doing co-occurrence statistics, if two nerves fire at the same time, but not always at the same time, but close to always, they should be neighbors. And based on how similar they are, you can have a distance between them, right? And just by having a measure like this, you can generate a map of your body surface. And once you generate this map of your body surface, what you discover is that body is two-dimensional. Right? It's a discovery that you make just by doing statistics over co-occurrence of signals in the body. And the body map is exactly the thing that is two-dimensional and connected. Right? There is other maps like the retinal map, but it has different statistical properties than the body map. And just by organizing these impulses that come in, by these statistical properties, the body is being discovered. So the way in which you discover your skin, the nerves on your skin, is not due to the wire that comes in. It's not there's a specifically red wire that comes in from skin neurons into the brain, and the brain looks at the red wires and says all the red wires need to go here. No, it only does statistics over all the impulses that come in and says, oh, there is a certain statistics type in all the signals that come in. So let's group all those wires that carry those types of statistics and those neighborhood, those relatedness into one brain area. And then in this brain area, make a map of the neighborhood, right? And what you get is a two-dimensional embedding space of impulses that can happen on your body surface. It's a very simple statistical learning algorithm that can happen in a self-organizing fashion just by local activation. The interesting thing about the brain is that it doesn't have a central control. There's no CPU in the brain. The brain is a collection of single-celled organisms that all try to survive. And the way in which a single-celled organism in your brain survives is by being useful. And it's useful if it fires at the right time. So what the brain is doing is it is trying to figure out which neurons are firing at the right time and give them a reward. And those that don't fire at the right time get a warning. And if they don't heed the warning, they are fired, which means they're killed. Right? So the way you survive in the brain, if you are a neuron, is to figure out what you're supposed to do, which is to fire at the right time. So you're looking for configurations in your environment that signal anticipated reward, which means you will be fed in the future. It's like being part of a company, and you are trying to not get fired from the company. And for every individual action that you perform in the company, you don't know whether it's the right action or not. And the company also doesn't know. But the company is going to keep track on what you do in the aggregate and tries to find a measure of whether useful in the aggregate. And every 2 weeks, you get a paycheck, which tells you are still on track. And if that paycheck ends, you are in trouble. Right, so you have to anticipate strategies to make sure that this is not happening. And in this way, basically, all the neurons in your brain are part of an organization that is forming itself to perform that evaluation, to evolve some form of local management and structure to make all that happen. And in this way, your brain is something like a company and some kind of investment bank that is trying to determine which values the different deals have that you can do with reality and how to execute on those deals. So back to the embedding space. In Word2Vec, a similar thing has happened in your body map, as I just described, was done with words. And what was discovered is that the resulting space doesn't have 2 dimensions. Words have many more dimensions of meaning. You need something like 30,000 dimensions. And what you then discover is if you draw a vector space where you basically give a location to every word in that space, that you find relationships between them. If you draw the vector between man and woman, it's the same vector as between king and queen. Right? What you now discover is that this vector is this gender relationship that you have discovered in that embedding space. Or here another one is the relationship between big and biggest is the same between small and smallest. Right? It's a certain kind of vector that exists, and if you use this vector to go from one word to another, you basically are able to move through this embedding space and perform regular operations in it. And this was a significant discovery. And when I saw this in a talk by Joshua Bengio, I thought this is amazing. We should be able to take any kind of representation, not just words, and put them into these embedding spaces. And this is, in some sense, what the transformer algorithm achieves, not just for language, but for arbitrary representations. So if you think about what it means for 2 concepts, or for 2 mental representations to be related in your mind, first of all, they can be in the same conceptual neighborhood. And I think of concepts as the address space of mental representations. The concept itself is just a pointer. The concept doesn't do anything, right? It's something that has no properties. When you think about abstraction in your own mind, the least abstract things are impulses that come in from your sensory neurons, or the differences between how things should be. Right? It's a step above that, because you filter out just signals itself. You look for change and differences. But so the difference is basically the smallest unit in such a system. And discernible differences, this is how we define information. So we start out with very, very basic information in our mind. And then at a higher level, we organize these information patterns, these differences, into features. And features describe how reality is changing in the aggregate from moment to moment. And these features are arranged into objects. And objects is what remains stable if the perspective changes. Right? So you can look at objects literally from a physical different perspective, and the object looks completely different, but it's still the same object because you combine all these different visual features that are visible at different times into one object to make sense of it. So the object is a more stable representation that combines features into a stable thing. And the concept is more stable than the object. The concept is abstracting over all the objects that can be part of that concept. And the concept still exists even if the objects all die. The concept is still there in your mind. You can still conceptualize it even if that thing doesn't exist anymore, and even if it never existed. It's the most abstract form of object. Right? It's just a pointer to different objects in the same way as objects are pointers to features that themselves can be objects. And so once you have this conceptual neighborhood, you can organize concepts in an embedding space, and you get 30,000 dimensions or something. And they this embedding space, and they tell you how objects are similar to each other across different dimensions or along different dimensions. By highlighting different dimensions, you can, with respect to the context that is established by these dimensions, determine how similar two things are on this conceptual level. Another thing in which they are related is the direct relationship path. So for instance, there's a particular way in which the concept up and the concept green are related. And that's because they are both part of the domain of extended things. And up is a relative change in direction based on some up-down dimension that you have if you have a sense of gravity due to your vestibular sense. Right, so you need to organize space with respect to this up-down direction, then you have this up relationship. And inside of that space, you have visual objects, and green is a stationary dimension in a color space. Right, so it's a particular kind of way in which you can make sense of textures locally in this visual domain. And if you think of your perception as some kind of graphics engine that renders reality in your mind, like it's rendered in Minecraft, but only in your brain, then there is a certain relationship between the concept of up in this graphics engine and the concept of green in the graphics engine. And this is all the way in which the computational graph in your graphics engine needs to be related to produce a dynamic simulation of reality. Right? So this set of relationships that combine all the different parts in the way in which you create reality. That's the relationship path. Another one is mutual information. Mutual information tells you how well two concepts predict each other, or two things predict each other. And this has to do with this basic co-occurrence. How often do they co-occur in reality? And if you do enough statistics over this co-occurrence, you can infer the conceptual neighborhood and eventually the relationship path, as GPT-3 demonstrates. Another one is the change distance. If you have one object and you have another object, what kind of changes do you need to make to turn one into the other? So what do you take away and what do you add to make that other thing? So for instance, when I try to understand other people, I try to understand which bits do I need to flip in my own mind to become that other person, right? So which traits, which beliefs, which biographical events, and so on, would I need to change to be that other and see the world from their eyes? And basically, this is possible, at least in an abstract sense, for any type of pair of objects. Right? So you can construct a path between them just by the set of transformations that you need to do to turn one into the other. Another one is the parameter distance. If you have two similar objects, for instance, a golden cup and a glass cup, then you have parameters that you can change. For instance, you can increase the transparency and decrease the metallic features of it, and you can make that continuously or discretely. And as a result, you can determine similarity based on these parameter changes, right? But this happens only within a single object category. These are examples of how we can establish the connection between objects. And now if you combine all of this, the entire set of objects, into one conceptual universe, you have one big embedding space, one big function that describes the entire reality that we believe to be part of. The reality that we believe to be part of is not out there. Out there is only patterns. The universe throws patterns at your systemic boundary. Your mind tries to discover a function that relates all of these patterns to each other with one or multiple of these criteria that you see here. And the resulting graph that emerges in your mind, that's meaning. Right? To discover meaning means that you establish a relationship between a feature or pattern to this function that you could call the universe, the whole of what exists and can exist. Your entire mental universe, that's meaning. It's the unified model of reality that your mind is constructing. And once you are able to establish connections from an arbitrary concept or domain or pattern into this function of reality that your mind is constructing, this unified function of reality, you have discovered meaning. And if you're unable to discover that relationship, the stuff is meaningless. So GPT-3 stands for Generative Pre-trained Transformer, and it uses this attention algorithm that figures out what to pay attention to in any given context. And it uses predictive coding, which minimizes the surprise. And, yes, Mario, what do you want to ask?
Yeah, I was actually going to suggest, just because in general we have like blocks of an hour, and we stop for 5 minutes to give people the ability to tend to their physiology if it required. When it's a natural moment to pause, you let me know, and then I will just open. If
there is no natural moment to pause. Let's pause after this slide.
Okay, perfect.
It's amazing. So I thought that millennials just don't have attention span anymore due to the internet, but they also have small bladders now. Okay, poor kids.
Well, I mean, like, I've trained them. It's just that they've got the statistical regularity in the computing brain that, you know, every hour we stop for 5 to 10 minutes. And so basically,
how about you? Can you not train your minions to have an attention span of 8 hours or something? I think it's enough to go to the bathroom once a day. I think you're just clearing out your kidneys this way.
You know, they don't repress me. It's just something I do, like how to just...
I think we are already sufficiently diverged. Guys, take your break. See you back in 5 minutes.
Okay, good, great. I'm enjoying myself tremendously. So actually, let me pause this.
GPT-3 uses a predictive coding paradigm. So it's only looking at how to continue a sentence, and it doesn't look at relevance. When we learn something, we don't try to learn all the possible continuations of sentences. We try to learn the underlying structure, because otherwise that would not be maintainable for us. So when you learn a mathematical text, you don't memorize the text in the book, what you do is you try to learn the minimum set of ideas that allow you to regenerate all the other ideas in the book, right? So I try to learn those things that allow me to make the greatest deal of inference. And this allows me to end up with a very sparse model of reality with relatively little data. And the models that you get with GPT-3 are very large. They are too large to spell out in such a way that the human being could internalize them again. GPT-3 knows more than a human being can learn in their lifetime. It has encodes more knowledge. But this knowledge is largely about style. When we start learning about things, we learn this indexically by directly interacting with the reality before we can think about it. And then we point at the things that we classify in that interactive reality, and our needs that are connected to it, pleasure and pain signals that we generate while interacting with things that generate relevance. And then we extend this into a notion of syntax, so we understand the language that we use to describe reality. And eventually we discover style as the long tail of this, and we can express ideas in different styles. But GPT-3 does it the other way around. It first discovers syntax, and then it discovers the style. No, it actually starts with the style. It starts with how the patterns look like. And then it discovers syntax as a regularity in the style. And then it discovers, finally, as the long tail of syntax and style, the semantics. So the more it learns, the better it gets at semantics, but it starts out with being good at imitating the shape of the patterns. Right, so quite different from the way in which we learn. But what's really great about GPT-3 is that it works over arbitrary content. And so the question was, would this also work over images? And before the transformer algorithm existed, there was already a way to learn the structure of images. And this exploits the fact that adjacent pixels in videos or in images are semantically related. Right? The closer they are to each other, the more likely it is that they are related. So just by grouping stuff hierarchically based on the neighborhood and then tuning these filters, you can learn. And this is a convolutional neural network. It basically uses filters that are based on the neighborhood of pixels and build them into hierarchies and tune these filters to model the distributions of adjacency in the real world, and thereby also learn perspective and so on. But this approach doesn't learn this work with language, because in language, symbols can be very far away, and there are many more types of symbols, and these symbols are not organized in a linear fashion, which means if you take two words and interpolate between them, you don't get a meaningful word for the most part, right? If you interpolate between the words little and the, there is nothing interesting in between. And so every of these symbols is a different symbol that are discrete, right? They have to be stored in discrete alphabet. And once you've done that, you look at the neighborhood between them, and sometimes the neighborhood is not adjacent, right? The and little can be adjacent to each other, but there can be also many, many words between the and little, and they are still related. So to discover that, you cannot use these neighborhood convolutions. And the transformer is the way to make statistics over the statistics context dependent that allows you to discover the structure. So NLP, because the convolutional neural networks didn't work on it, forced people to come up with new ideas. And the transformer, therefore, was discovered in natural language processing. But the transformer also works on images, and it's going to discover convolutions, the algorithm that we had before, as a special case. So GPT-3 has some limits. GPT-3 is not entangled with the present environment. So it's not in real time, and it doesn't know its context. It's just dreaming. And it has retrograde, interrograde amnesia. It doesn't know what happens outside of its working memory context. It forgets everything as soon as it loses its working memory context. And it's not able to learn anything in real time. It's only going to learn in this batch processing and a large parallel process with lots and lots of training data. It's not learning from its inferences in real time. So it would need to be extended to do that, and probably different learning algorithms. And there is this question, is it possible to ground that in perception? So does this linguistic learning scale into perception? I remember when I was young in Osnabrück, our linguist had grave doubts that you could learn meaning just from language alone, from symbols alone. You wouldn't need to have affordances and interacting with the real world. But then latent semantic analysis came up, LSA, which does the statistics over the word and was already starting to discover structure over language. So I started to doubt this idea of the linguist that symbols are insufficient to discover any kind of meaning. And GPT-3 shows that just by using language, if you use enough of it, you can already constrain the space of universes a lot. Right? So there are not that many universes that contain our Wikipedia, with all the articles about physics, biology, and so on. If you are able to parse all this, basically you constrain the possible universes that you can be in very, very far. We could even build a robot in principle that uses GPT-3. So you'd have this environment, you take a vision module that translates what you see in the environment into text, and they use it to prompt GPT-3. You basically generate a string that tells that asks GPT-3 to complete it, and what you tell GPT-3 that it's a robot that is in the context of what you see in your environment, and ask GPT-3 to continue what the robot is doing next. And you take the output of that thing, translate it into actuators. The actuators act on the environment, and the vision module closes the loop. Right, so you have a system that is continuously acting on its environment. This is a toy example that I only used to explain how this might work, but 3 months later, somebody actually built that.
Yeah, I'm not surprised. I mean, like, I am expecting people to come up with GPT-3 for NPCs in any game, really. Like, I am surprised that it didn't happen yet.
The very funny thing that people did was on Twitter, they did GPT-3 death matches. You describe in the prompts 2 different superheroes or characters or weird phenomena, and then you describe how they enter the arena and fight to the death. And then GPT-3 is going to generate the fight for you based on the properties that you initially specified, and you see who's going to win.
I remember those unwanted superpowers, like, you know, grow hair everywhere or become invisible when no one's looking,
yeah, you can build all these things in your characters and see how this pans out in a fight. And GPT-3 is quite creative and coming up with interesting solutions. And it's also creative with respect to the real world. So when people built a robot that was operating in a lab kitchen, they did this, the actual coffee kitchen of their lab, and asked the robot to help with things. And so, for instance, there was a water spill, and the robot needed to figure out what to do. And it was using the description of the situation, and it was generating sequences of things that it should be doing, like looking for a sponge. But the robot didn't know how to look for a sponge. So it was throwing this again into GPT-3, and GPT-3 was spelling it out until it got to a level where the robot actually had the actuator commands. So in some sense, GPT-3 was used in its original form without additional training as Stack Overflow for robots, right? The robot doesn't know how to program reality, and it can use that thing to answer questions about reality until it's broken down to a level that the robot is able to act on. But classical AI, as we all know, failed, right? Symbolic AI of Minsky in the Minskyan way didn't really work out. And Ludwig Wittgenstein anticipated this. At the end of his life, he had not just preempted Minsky's program, but also Minsky's failure. And he did this in the philosophical investigations. And in the philosophical investigations, he basically expresses his despair about dealing with imagery. In the original Tractatus, he has images there and the pictures, and he hopes that he can define operations over the pictures. But eventually he figured out that there was no way in which grammatical language was able to generate pictures from patterns, at least not any way that he could see. And this was the same problem of symbolic AI. And this is the problem that deep learning is solving, right? It deals with the messiness of reality with unprincipled reasoning that is able to give you results even if the result is not logically exactly true. And it does it by approximating arbitrary functions. And when you give it patterns, creates functions that are able to predict these patterns and find regularities in them. And this works so well that you can use these pattern matching algorithms, these function discovery algorithms, function approximators on grammatical language, and you find better solutions than you do with analysis with Chomsky grammars. They discover something that is quite similar to these grammars, and but it's a superset of them. It's something that can do these grammars, but it can also do all the exceptions, and also many of the potential exceptions that it hasn't seen in the training data yet. So it can discover new words, for instance. You can give it examples for new words and then can give in a similar way, new names to things that don't exist yet or that don't have names yet. Or you give it new names for objects and it can give you a hypothesis what object that could refer to. But when we think about perception, it seems to follow different principles than grammatical language. In our own mind, we find that perception is largely about geometry and coherence, and analytical thought is about dealing with reason, dealing with nonlinearities, making things arbitrarily compositional and systematic, and so on. So how do we solve perception? Perception, as I said, is geometric. Reasoning is discrete, systematic, compositional. And how can we get geometry? As we've seen initially, everything can be done with automata. So how can we create discrete automata that give us geometry? And when we enter a school, we typically think geometry is easy because it's directly given in the way in which we interact with reality. And when you try to derive geometry in mathematics, and typically you don't do this in school, unfortunately, you do this later in your studies, basically all the geometry is taken away from you and you need to rebuild it from scratch. And you do this by first discovering numbers. And the easiest way to describe numbers is to say that they are a subsequent labeling scheme. They're just a way to give labels to everything in the world and to have a new label every time and make sure that these labels are ordered somehow. Once they're ordered, you can define a predecessor and successor operation, which means go to the previous number or go to the next number. Right? It's just a label. That's all there is. And then if you apply this successor or predecessor operation multiple times, a number of times, you have addition. And what addition allows you is to travel on the number line, not just to one step forward or backward, but to teleport on it. You basically can jump around on the number line, right? And now if you do successive additions, a number of times addition, you have multiplication. And what multiplication allows you is to zoom in and out on the number line. Right, it's pretty cool. There is also a relationship between addition and multiplication. There are basically two spaces that you now get, the addition space and the multiplication space. And if you want to translate multiplication into additions, you have a new operation that's called exponentiation. Right, exponentiation is exactly that. It's the relationship between addition and multiplication. So this is all the basic arithmetic there is. There's not much more. And what you can now do is you take your number line and you want to make it two-dimensional. How do you get to 2 dimensions? Well, you fold your number line into a lattice, into some kind of regular grid. And a simple way of doing that is to define operators that don't just do the successor to the left or to the right, but also to the up and to the down. And you go to the left and to the right by adding or subtracting 1 from the address, your address space, and you get to up and down by adding or subtracting a large constant. Right, so if you add 40 or subtract 40, you now have an array where you have 40 rows and you have columns. Right, and you can jump between columns and rows by adding or subtracting 40 and by adding or subtracting 1. And in this way, you can move in the X and Y direction until you hit the boundary of your array. You can also define other functions that don't have a boundary. So there are ways to make that unlimited with slightly more clever operators. You can also define operators that work in 3 dimensions, 4 dimensions, and so on. And a nice property of these multidimensional numbers is that addition and multiplication still work on them. So basically, if you add 2 two-dimensional numbers, you add 2 vectors. And now you basically teleport around in the vector space in 2 or 3 dimensions. And if you multiply this two-dimensional number with a single number, you zoom in and out. If you multiply it with different numbers in the X and Y direction, then something very, very interesting can happen. If you define complex numbers, you can now define rotation. Rotation is an operation by which an object stays the same if you move it across dimensions. And it's a very interesting mathematical property that this exists, that you can define grids in which you can rotate objects. And such grids exist in 2 dimensions and in 4 dimensions and in 8 dimensions. That's it. So you can, from number theory, derive what kind of rotations are possible, what kind of operations you can make in spaces. And spaces are basically the way in which you can organize too many parts to count into an extremely small grid, into a grid that is so small that you cannot see the individual grid lines anymore. And once you define such a grid and operators over it, then some operators have an interesting property, which means if you apply them infinitely many times, they have pretty much the same result as if you would apply them quite often. It is not always the case. There are many functions that give you a very different result when you apply them quite often or infinitely many times. So for instance, when you put money into your bank account, you do this quite often, you get a very different result from doing it infinitely many times. Because there is a linear relationship, right? But sometimes the relationship is in such a way that it approximates a certain target value, right? So there is, if you would, for instance, divide numbers by 2, and you do this very, very often, you get the same result as if you do this quite a number of times. Right, so some operators have this property that when you evaluate them as a series, when you add more and more steps to that computation, you get closer to the same result, to a convergent result. So you can often find an efficient approximation for that thing if you have too many parts to count. And geometry is exactly that domain. Geometry is the domain where you have operators over too many parts to count that converge. And what your brain is doing, it discovers these operators, and it's awful. It takes months. It's really hard. And these operators are so complicated, it's very hard to reverse engineer them. It takes many years of study. And before that, it takes a millennial of uninterrupted intellectual tradition to figure out how to define languages into which to reverse engineer your thinking. And it took me a long time to realize that mathematicians are mostly talking about stuff that my brain is already knowing how to do. Right? All this geometry, my brain knows how to do it. All this probability theory, my brain knows how to do it. And I just need to figure out what part of mathematics the formalism is pointing at in my brain that already exists. Right? My brain has discovered a language in the interaction between neurons that allowed it to formalize geometry, to discover these operators that allow us to make sense of the world of too many parts to count. So geometry is actually hard. And explaining geometry in a grammatical language is very difficult. So building a 3D engine from formal programming language takes many, many decades. But what you can also do is you take the transformer algorithm, and instead of feeding it with text, you feed it with images. And what you get is a model of the world that fits into something like 2 gigabytes. That is at least the case for the current weights of Stable Diffusion. And these 2 gigabytes contain all the faces of all the celebrities and all artistic styles that it has ever seen, and all the spaceships that exist in popular culture, in historical events, and so on. It all knows these 2 gigabytes. And you can evoke the content by giving it a text prompt that is then piped through a language model. And the language model maps it into an embedding space, this high-dimensional, 3,000-dimensional space of meanings. And this 3,000-dimensional space of meanings is then mapped by a learned transition into the space of meanings per images, which has the same shape. Right? The space of meanings that is discovered in the language model is the same space that is being discovered by the image analysis models. And I think that is the proof that you can learn interaction from language. That symbols are enough because the space is the same. There are a few things that are not the same, but the overlap is so large that these models can learn how to translate language into images without having ever interacted with the world. Just by looking at artifacts that people left behind in the internet, only statistics in the artifacts generated by human beings. So this picture that you see here is generated by DALL-E, and it's just asking to generate a number of cups and bowls and so on under different lighting conditions. And it can do that also with correct shadows and so on. You can, I did examples where I had a Ming area Chinese dragon reflected in a spherical mirror, and it got that right. So it understood ray tracing to some degree. And that's completely fascinating to me. There's also a recent work which is creating 3D meshes from a 2D transformer. So it only takes the 2D images that transformers have seen by seeing most of or a substantial part of the internet, and then uses this as constraints to generate 2D meshes of objects, 3D meshes of objects that you can import as assets in your 3D program. So just using the transformer algorithm on images, 2D images, you are able to reconstruct 3-dimensional worlds and lighting and perspective and so on. And one of these embedding spaces is I gave as an example, our body map. And this body map is in an area that forms in the somatosensory cortex. And it's one that does statistics over the neighborhood of nerves. And it turns out that you have an extremely high nerve density in your face and on your tongue and on your hands, but a low nerve density on your back. And as a result, you get these deformations of this homunculus. If you look at the map of where the different parts are mapped into the somatosensory and motor cortex, you find that the areas that have high resolution take up a lot of area, and the parts that have low resolution take up a small area. But later on, you learn to touch yourself. You also do this in utero, and once you are born, you also touch the ground. And this allows you to learn a second map that normalizes the first map in space. So you basically have multiple maps that are stacked on top of each other, hierarchical embedding spaces that tell you how to step-by-step make sense of reality. And outside of this map of your body surface that is normalized, you have a map of objects that touch your body. That is in the same normalized space as your normalized body. So they are in the same frame of reference. And at some point, you learn that the space of objects that you can touch is the same space as the objects that you can see. And at this point, basically, these representations merge and become multimodal. And these multimodal representations also what GPT-3 and DALL-E discover. If you look at how GPT-3 computes, after the first few layers, it has completely abstracted away from sentences and languages and goes into a space of meanings, and it performs the operations in that meaning space and then translates it back into the space of language. It's quite interesting to see. So if we were to build a GPT-3 robot, we want to have a perception that is also learning. So basically, we take this reflection module that is generating a story and a multimodal framework, and then it generates expectations, and these expectations are compared with the perception, and this should give rise to online learning. In addition, we probably also want to define a context that is given by motivation. So there are some regulation targets that the system needs to fulfill, so your robot gets a direction for what it learns and what it acts on. And once you have that, you probably have an agent that is of a similar class as us. And what's at the moment is not clear how far we are from that. And I suspect that we might be closer than many people think. I remember when I lived in Berlin,
Less than 400 years.
Artificial general intelligence was never going to happen. In Boston, it was always 30 years away, and San Francisco is always 10 years away. But it's always been like this.
Yeah, it's definitely not 400 years.
Yep. So if we build a robot that is able to discover itself, it needs to notice its own existence in the world. That's basically the first stage of the self model. And you discover your body not because it's immediately given, you discover it as part of a loop between your intentions and the outcomes of your actions. Right? Without being able to observe your own intentions and the outcomes of your actions, you're not able to discover that you have a body, which is the instrument between them. The body is not given by itself. It's just a thing that you discover in reality. And your own self is something that you discover as what you are. And what you discover is that you are an attention model, you are an observer, right? Atanas.
I think this slide was going to answer my question. Essentially, about the phenomenology of questioning your existence and where does that fit in these models?
Yeah, so the next thing that you discover after you discover your self model is that you need to discover epistemology, which is the criteria under which something is true, which means also that you have to discover the nature of language and you have to discover what meaning is. You discover that meaning doesn't refer to objects in the outside world. You have to discover that what you take to be the outside world is actually generated in your own mind. And it's something that our culture consistently gets wrong. We basically teach kids at school that what they see is what they interact with is the physical world. But it's not, right? The physical world is quantum mechanics. It's pretty unintelligible. And what you see is game engine that is generated by your brain to make sense of the patterns at your systemic boundary at a certain time frame and a certain resolution using a certain number of recurrent layers in your brain. Like, this is what you get to see. You don't get to see anything but that. You only get to interact with your own mental representations ever. And these mental representations are basically a dream. And that dream is generated by a mind on a higher plane of existence in the parent universe. And that parent universe is physics. And the mind on the higher plane of existence is generated in the skull of a primate. Right? This is all correct, but it's not what you experience. What you experience is the dream reality. We live literally in a dream. And that's why miracles are possible, because it's possible to edit the dream using suitable techniques. It doesn't mean that you can edit physics. You have to pay a price for magic, but you can edit your experience. You can change your experience, because your own experience happens at the interface between a simulated person and a simulated world in your own mind. Right? The simulated yourself is also not the brain. It's not the algorithms that run on your brain to produce you. Yourself is a person inside of that brain. And once you have discovered epistemology, the criteria under which something is true and how languages work, you can go on and to reverse engineer your own functionality. And this project, in some sense, is Turing's project, right? Your Turing test is not just to build a machine that is able to convince a jury. It's able to build a machine that's able to convince Turing, which means it's a machine that needs to be at least as smart as Turing. And if Turing is smart enough to build an intelligent machine and knows how it works, then this machine needs to be able to explain to Turing how it works. What it turns out is what Turing has as a hypothesis is that humans are generally intelligent. It's an unproven conjecture. And to prove that conjecture, we need to reverse engineer ourselves by building an intelligent machine, which means to reverse engineer ourselves to the degree that we're able to understand how we work. So to complete this GPT-3 robot, basically what we have is a perception agent, an attention agent that is coordinating perception and attention in that perception agent, and a motivation agent, and they interact with each other. An area that I think needs to get some attention might be language of thought. And while Fodor's notion of how a language of thought is to be defined, I think was wrong. And the idea that language of thought is somehow in contrast to imagery is also wrong. There is a difference between the language that we use for perception. For instance, in perception, you don't have arbitrary compositionality. For instance, you always have textures superimposed on geometry, not the other way around. Like in a game engine, right? The texture comes below the geometry, and the movement comes above the geometry. Right? So there is a certain way in which you can fit these functions together to make things work in your perception. Otherwise, the game engine wouldn't work. But that's not true for concepts. You can imagine a nose that is on a face, and then there's a face on the nose, and there is another nose on that face, and so on, right? So you can have arbitrary compositionality in the conceptual frame. The languages that we use to reason allow us to manipulate perception in arbitrary ways. And to make that happen, we need to have a language that is in some sense unified. And I suspect what happens in our own mind is that consciousness is some kind of imperialist principle that emerges relatively early on as a result of what Gary Edelman calls a neural Darwinism. Right? So the way in which our brain is organized is not entirely encoded in genome, because our genome is relatively short. It's like fits on a CD-ROM, and only a small subset of the genome codes for the brain. It's probably just a few hundred kilobytes or so. And of these few hundred kilobytes, you cannot implement a connectome with this and sophisticated mental organization. But what you can do is you can define a bunch of cell types, an initial layout of these cell types, and some overall switches and biases in the system, and set up an evolution. And now what happens is an evolutionary competition between different modes in which your brain could be organized. Right? A hierarchy of control and power that emerges in your brain, like it emerges in a company that you are starting, or in a society that you are starting of individuals. And for every situation that the organism is in, and the type of organism that needs to be controlled, there is an optimal organization with respect to speed and generality and able to make inferences and to solve problems. And the evolution is trying to approximate that. And you only need to rig the evolution so it converges quickly enough. And it's a very efficient way to define mental organization. And the way in which that happens, I suspect, is that you need to have self-reflexive attention. So you start out with, in the same way as a government that is effective is a sentient government. It's a government that's aware of the fact that it's a government, and it has a notion of the system that it wants to govern, and then imposes this structure on the system. And it tests which impositions of structure work, which type of bureaucracy work, which type of colonization works. And basically every country that you see is the result of a colonization of initially bandits that are farming farmers, or farmers that get rid of the bandits by creating a standing army that then starts to farm the farmers. The outcome is the same. You have an aristocracy and farmers that are being farmed by the aristocracy. And this is your agricultural society in which you have a large group of domesticated people that are controlled by a small group of people with guns. And eventually these gangs that farm the farmers consolidate, and they form hierarchies, and they form empires. And an empire is basically an algorithm that is imposed on existing social structure that is more efficient than the previous social structure, and that it's able to extract more energy from the system than it requires to impose that structure on the system. In this sense, every organism is also a colony on the environment. And every brain organization is a colony on potential other brain organizations, right? It's the one that wins out. So this idea that you have an organization in your mind that starts out with some form of governance, with some kind of conductor that organizes the mental orchestra to make sure that it's just not just playing free jazz, but is completely coherent, that requires the imposition of some kind of language of thought, I think. A language that allows the entire system to talk to each other and relate all the different parts of the mind to each other in a single framework. And this language of thought is not like natural language. It's executable, for instance. So you can use it to think in it, to construct natural language in it. You can observe other people when they speak in a language they're not fluent in, how they construct this language, not using their previous language, but using this language of thought. Or when you observe yourself programming, you use that language of thought when you do pointer manipulation at mostly. And it's universal. It can work on all types of representations, both on perceptual and on reflexive and abstracts. And it's able to do retrieval and construction, manipulation, disambiguation. And it's not learned. It's not nobody teaches us how to think. We discover that. But we discover it before we have a self. So it's very hard to see that thing unless it breaks. If you manage to break it, for instance, by waking up in the wrong order in the morning, you might, or by getting severely intoxicated, you might notice how your consciousness, how your perception and so on fall apart in systematic ways, and how your brain is trying to recreate that. Some people have that experience after a stroke, where they basically are conscious and organized and reflexive, but the language of thought doesn't work, and reality makes no sense. And they discover this process of reorganization until it clicks again, and the language of thought works again, and can navigate the embedding spaces again. There's also another thing that I want to leave you with, and this is the possibility to go beyond Turing machines. There are basically two paradigms in computer science. One is the deterministic Turing machine, and the other one is the non-deterministic Turing machine. And the difference between them is not that the non-deterministic Turing machine is random. They're both deterministic in a way, so it's a little bit confusingly named. The difference is that the deterministic Turing machine goes from state to exactly one other state. That your computer goes from one state exactly to one other state. It's always in only one state at a time. And it can branch between states, but it's only going to go to one branch, right? It's going to evaluate a condition, and based on that condition, it's going to go into exactly one state. So the Turing machine always describes a sequence of steps. And the non-deterministic Turing machine doesn't have to go into a single state. It doesn't have to decide for a single state. It can use a simpler definition, fewer constraints. And with these fewer constraints, it's not able to determine which state it is going to go in. In the solution, it goes into multiple states. So it's branching. if you think about it, you can obviously implement the deterministic Turing machine on top of a deterministic one. You just make sure that you constrain it so much that you only ever go into one state, right? So the non-deterministic Turing machine is a superset of the deterministic one. But it also works the other way around. You can always emulate a non-deterministic Turing machine on a deterministic one by just making sure that you revisit all the branches. You just put every branch on a stack. And you make sure that you go down all the branches. But what it means is that the deterministic Turing machine can be very inefficient at emulating the non-deterministic Turing machine. So if the branch space goes very far and wide, then with every step, the deterministic Turing machine gets slower and slower. And that's the thing that we observe in our universe. Our universe seems to be a non-deterministic Turing machine, which means that when the universe doesn't know in which state to go, it goes into all of them. So we live in a multiverse. But you and me, we only ever going to visit one branch, right? So in every step, we get only projected into one of the future branches in the universe. So from our perspective, the universe looks like it's only following a single path. And the computers that we are building in our universe rely on parts of the universe being able to predict other parts of the universe. So we can only rely on a deterministic subset of that non-deterministic Turing machine. The non-determinism of the non-deterministic Turing machine is the result of us not knowing which branch we will end up in. In reality, we are in all the branches, different copies of us. But these copies are never going to meet again, right? These branches don't merge. So as a result, you don't know which part of the non-deterministic Turing machine you will be ending in. But if you could see it from the outside, you would see that copies of you are in all the branches and all the branches are being visited. And so from the perspective of the character in Minecraft, it doesn't know what's going to happen around it. It cannot predict it because all the branches will be visited, but itself, this process will only visit one branch. And the beauty of the non-deterministic Turing machine is it can also perform computations, and these branches can functionally merge. If you take every of these states in the branches as a bit pattern, then not every branch is going to end up with a new bit pattern. Very often different branches will lead to the same bit pattern. When that happens, you can predict statistics of the universe. Right? For instance, you double slit experiment, you cannot predict which branch the photon is going to go. You don't know whether it goes to the right or to the left slit. But for 1 million of photons, you can predict the statistical properties of those photons going through it, right? So you can predict at some level of granularity what the bit vector is going to look like. And this is what you can use to make the universe predictable and controllable for us. And so we live in the subset of the controllable universe. The beauty of that is the universe can be defined without priors. You don't need to have this explicit set of physical laws. You can just apply all the operations, and when multiple operations match, you branch. So basically, it's a more efficient way for the universe to define itself without having any priors. But now think of the brain. Is the brain deterministic, or is it a non-deterministic Turing machine? So is it a system that is going to go from one state into another one, or does it go into a superposition of states? Of course, the brain is, for all means and purposes, a control system, so it has to have a classical implementation. It's a classical system at heart. But it could be a quantum-like system that is implemented on a classical substrate, which basically means it pretends to be a non-deterministic Turing machine stochastically by having enough neurons that do other stuff. So it is going into these superpositional states. And this is an idea that has been, for instance, explored by Jerome Busemeyer. And Jerome Busemeyer maintains that our mental representations are actually superpositional. And I find that very plausible. Imagine a horse next to a tree. Is the horse left from the tree or right from the tree? But we don't know. It's a probability cloud. But of course, the horse is defined in such a way that it can only be to the left or to the right, or in front or in the back. It cannot be simultaneously in several positions around the tree if we only mention one horse. So if you attend to the horse around the tree, even in your imagination, you collapse the representation by attending to it, right, into a classical one. The horse is, when you attend to it mentally, going to be to the left or to the right. But as long as you don't attend, you are in the superposition. And you can make inferences based on that superposition. And to express the mechanisms in which we do these inferences formally, we need to use formalisms that are very similar to the ones in quantum mechanics. Not because the brain is literally a quantum computer, but because it works like a quantum computer, because it works like quantum universe at some level. So this basically gives rise to a different class of languages that would need to be explored in the context of a language of thought that are slightly different than the languages in the Chomsky hierarchy, because they don't work by deterministic applications, they work by indeterministic applications, by this applications of operators in multiple branches and then seeing how they merge. This is a paradigm that I'm currently thinking about a lot. And I suspect it's a paradigm that our current language models are discovering implicitly, but that linguists failed to discover before. So this is what I want to leave you with.
Thank you most kindly, Yasha. Like this, we've been graced with a stream of thoughts that unlike any other that I have met.
I think our time is up, right? Or do we have
our time is basically up. I did want to have at least one or two questions, and I have one of my own. I'm gonna basically just start with two. So Chomsky, in the most recent book, like Why Only Us, he has suggested that binary set formation is the language of thought. And it can actually work also for, across modalities, like you brought it up. And I was wondering, I mean, like it doesn't have by nature this non-deterministic aspect, but you could easily put it in. So that's question number one. I mean, what do you think about binary set formation as like, you know, solving some of the problems of language of thought? And the second one, why quantum and not statistical? I mean, like you're creating distributions ultimately, like of the horse on the left and on the right. So these are my two questions.
So the one is, how do you describe the distributions in which you operate? It's not a completely probabilistic system, but it's one that basically alternates between the superpositional state and collapses of the superpositions. Because when you make control models, you need to make classical models in a way. And I think this interaction between superposition and collapse is characteristic for the quantum mechanical descriptions. So of course, they're subset of the probabilistic models, but it's a particular probabilistic language that would have to be used.
I was thinking in the context of Hopfield networks. We discussed them recently, and I was, you know, the states exist latently there, but if you're, say, for instance, finding out what's the best solution for a problem, and you're inspecting your own experiences via your brain, calculating non-deterministically what the outcomes can be, of say two, in a sense, I mean, it's doing that kind of preliminary trial computation to see what sticks, right? To see what conditions obtain. Yes. So, like,
the thing is, you cannot observe yourself thinking non-deterministically. You can only observe yourself deterministically, because the models that you are going to make are deterministic, because otherwise you could not reason over them. So basically, all the observations are going to be classical, but they're an illusion. In the same way as the classical universe is an illusion, right? The collapse of the wave function is the point beyond which the illusion doesn't work. It's the one beyond which you cannot pretend that the universe was classical.
Yeah, I'm going to open the question for the floor for other questions that are not mine, because I know that I could actually go into a big rabbit hole on that particular statement. Okay, let's crowd. I mean, like, I'm sure you've been overwhelmed in a couple of different ways, but did you accumulate some questions that you wanted to deal with now?
Atanas still has his hand up. I don't know if that's because he forgot to take it down.
Oh, sorry,
I think so. That's what I've assumed.
But if I can take the opportunity in that case, I kind of understood the whole computational nature that you were hinting at during your whole presentation, but I still cannot imagine how consciousness emerges, as in, assuming GPT evolves to the extent where we could call it conscious, would it still have this phenomenological experience that each of us has?
A super good question. Okay, I need to go into a couple more slides.
Good one, Atanas.
Basically, our Western world is quite confused about consciousness in ways in which many other cultures are not. And I suspect that's a little bit the product of Christianity and later on Enlightenment, which both basically Christianity indoctrinated people with a notion of reality that doesn't work, and Enlightenment tried to debug it in the wrong way. And the notion that we got out of this is this disparity between idealism, that we live in a dream, and physicalism, that there is a causally closed mechanical layer at the bottom. And the Western world is confused about how to put this together. And typically we have this Cartesian view, and most people are actually Cartesians. So basically there is the extended world with the objects inside of them, res extensa, and then there's the world of idea, res cogitans. And the res extensa is associated with physics, and res cogitans with mental events. And then there's the question of how are they related? And then people meditate or take acid, and they discover, oh my God, I am actually the universe. And so universe itself is conscious, and panpsychism is true. And what they discover instead is that the delineation between self and world in the mind is artificial. They're both in the mind. They both are generated by the same game engine. And this insight is very old, and it's actually part of our culture, and it's encoded in the story in Genesis 1. Genesis 1 has been appropriated by the Christians and turned into an origin creation story for the physical universe, right? The Christians teach people that Genesis 1 is the story of the creation of a physical universe by a supernatural being, which is ridiculous because it's epistemologically not valid, right? There cannot be an experiment that gives this result. There can also be no train of reasoning that gives this result. Nobody can know that, right? Everybody who tells you this story has no way of knowing that it's true. It's like with astrology. When I was a kid, I thought the problem with astrology is that there is no plausible causal mechanism that associates celestial events with people's individual fates. But when I got older, I realized the main issue is that the astrologers claimed that they had a methodology to establish that relationship if it existed. Right, but the astrologers had no way to collect data. They had no statistical tools. There was nothing at the disposal of the astrologers if astrology was true, by which they would have been able to discover that it was true. But this was never a valid claim. In the same way as talking to a burning bush is not a valid epistemology or a valid way to conduct inquiries about the nature of the universe. Right? There are other reasons why you would say that. But if you force people to believe that it's true for the reasons that you give them, you are forcing them to give up epistemology. And epistemology means that you have to accept that everything that is not impossible is possibly true. And the confidence needs to be shifted around according to the evidence that it's true. And so if we read Genesis 1 with correct epistemology, and epistemology is not a recent discovery. I think that our ancestors had discovered it quite early on because you just need to think straight. It's a slightly different story. And I think it's actually not a story about the universe creation, but a 6-stage theory of conscious experience and personal self-development. What happens in that story when you read it is that the Ruach Elohim, the creative spirit, is hovering over the surface of the water, and then it creates a firmament that separates the waters above the firmament from the waters below the firmament and stuff like that, and it all makes no sense. And I suspect the word that was mistranslated here as water is actually substrate. So let's revisit this. We have a creative spirit that is forming over a substrate and hovers over the substrate. And the substrate is without form and void. There is no world yet, just chaos. And the first thing that the creative spirit discovers is how to make light. Not really light, contrast. It makes that contrast by getting oscillations out of the neurons in a targeted way, and associating the intensity with brightness and the flatness with darkness, with the color of the day and with the color of the night. Now it has a scalar dimension, which it can create difference. And then it can take that difference and apply it to representing spatial regions. And what it also does, it separates res extensa from res cogitans. Res extensa is the world of the world model, right? It's the model of reality, what is the case outside of you. And then the world of ideas. And these are separate domains of the same mind. Res extensa and res cogitans coexist in the mind, not one in the world and one in the mind. They're both parts of your mind. The world model is part of your mind. And next thing it does, it arranges these distances that it has discovered by taking a scalar value and evaluating it as an extension into multiple dimensions. So it combines multiple extensions into dimensions. And the first space that this covers is the plane. And the plane gets associated with the ground. And first babies only crawl around on the ground and they refuse to build towers because they cannot think in 3D. They only arrange things in 2D. And at some point, they discover the third dimension. They start to build up. And so they discover the sky over the ground plane and now have a three-dimensional world. And they discover how to populate this mental game engine with objects. So they discover how to model solids and liquids and organic shapes. And it's all described in Genesis. And then they discover illumination. They discover the constancy of shape, and they discover the nature of light sources, and they discover the big light in the sky and how it changes over time, and how things change their appearance in response. And then once that is done, it discovers how to construct all the plants and animals and people and give them all their names. Right? Again, the construction of plants and animals is not something that happens out in the world. It happens inside of the mind. And giving their names is also nothing that happens in the creation of physical objects. It's something that happens once you arrange all these patterns in your mind, you name them, right? You learn the names of these objects. So you learn the language that you use to refer to all these objects. By the way, all these illustrations are made with DALL-E, with this generative program. And the next one it discovers is that the purpose of the whole exercise is to interact with the world and to control it. So this creative spirit creates another spirit in its own image, but it creates it as man and woman. It creates it in such a way that it thinks it's a person. The creative spirit is not a person. Your mind is not a person. It's just a modeling system. But it discovers that it needs to model a person. It needs to create a personal self. And this personal self has, in some sense, the same powers as the original creative spirit, but it forgets them. It's not able to edit its own reality because otherwise it would cheat. So it thinks it's the person. It thinks it has social relationships. It thinks these social relationships are important. It thinks it's super important what other people think about it. It thinks it's very important what itself thinks about it, right? This is what makes it human. And this person emerges roughly around 2.5, 3 years old. And you notice that this is the age when kids start to consistently talk about this first person character from a first person perspective, no longer from the third person, and start to organize their memories from this new person perspective. So they have childhood amnesia. They don't remember the things that happened before, not because their brains are mushy. You can basically look at a young child, a toddler, they have perfect memories. They can refer to things. And then they suddenly forget all of that, things that happened before a certain crucial age. And I think this is when the new spirit takes over, the one that is created in the image of the first. And I think this is the reason why you have this confusing statement that God created people in its own image, right? It refers to that spirit, to the software agent that is built into the engine to perform the reflection. The neurons don't know what it is like to feel anything. They're physical systems. Brains cannot feel anything. Physical systems cannot have experience, right? This is correct. But it would be super useful for the brain to know what it would be like to be a person that feels something. So this person is created virtually, as if our experience is virtual. There is no person. There is only what would it be like as if there was a person. And what would that person feel if that person cared? And what would that person think as a result of those feelings? And what would it want as a result of having those feelings? And what would it do as a result of wanting these things and having this model of what it could be doing? And then we use the output of that model to drive behavior. And we are inside of that dream, inside of that model. And outside of that model, there is no consciousness. If you wake up from the dream, you would not be there. So I think this personal self is an intermediate stage that happens after you are well organized enough to discover that you have a self, but before you're well organized enough to deconstruct it again. So our personal consciousness is intermediate. And the older we get, the more we deconstruct our qualia. And I suspect that if we would be living for a few hundred years, we would not be conscious in the human sense.
What a tour de force. I mean, like, I hope that has taken you in, Atanas. Like, would you like any last words?
No,
I think these were good
thank you.
last words, right,
Thank you.
Atanas? Do you have any?
I'll need to integrate that. Thank you.
Indeed, I shall also thank you. I mean, like, this was an unexpected turn of events on a language on a level, but it somehow is so befitting. I mean, like, it wouldn't be appropriate without it. I'll make sure to you know.
I think it's a very satisfying train of thought. So I thought I'd leave you with it for this evening. And I wish you a wonderful rest of the night.
It's so fulfilling. Thank you for Genesis and what is the at all? I forget. Might be the next metaphor. I embrace you warmly, Yasha. Thank you for your time. Let's touch base and thank you everybody for sticking to the end. So. Yeah.